Hello everyone, and welcome to part 1 of the section 4.1 notes, where we are beginning our discussion of inverse functions. Now before we get into talking about inverse functions, we want to define this idea of having a one-to-one function. And one-to-one, the name here signifies what it's talking about. One-to-one means basically each one x value should be assigned to one y value and vice versa. Basically that x and y values are assigned uniquely to each other. And so the definition here as it's given, it can look maybe a little bit cryptic, this thing about the a's and the b's, but why don't we just break it down what it's talking about here with the one-to-one functions. We will say that a function is one-to-one if whenever you have two x values like a and b that are in the domain, so these are both x values, we have to have the fact that if those two x values are different from each other, a and b are not the same, then the y values that correspond to those x values also should not be the same. And so basically different x values result in different y values. And it's the same statement to state it this way, which this one's called the contrapositive statement. It's always the same as the original one. We will have, and this is actually what I would like to point out, is that this statement over here, this is how we would want to prove it with the definition. If you're ever asked to prove using the definition of one-to-one whether the graph of an equation or whether an equation is representing a one-to-one function, then we would actually want to use this statement, because it's much easier to prove this way than it is to prove the way with the not equals. Because not equals, don't really want to get into it too much about how the logic is working here, but it is much easier. You can just trust me for now that it's easier to check the statement that's given here, which is that if a function has the same y value whenever you plug in a or b as the x values, then it should definitely be the case that a is equal to b. So in other words, if we're able to get the same y values for two x values, then actually those two x values have to be the same. And so we can see here an example just from a set notation where this here is a relation. We would check before, whether this relation is a function, for example, by looking at the x values and saying if there's ever the same x value, then we should not have two different y values for the same x value. Here, since we're checking one-to-one, we kind of are looking at the opposite thing. We look at the y values and we're seeing if the y values ever get repeated. And so you'll see that actually here the y value of 1 gets repeated. And then when we're thinking about the fact that basically f of a equals f of b in this case, because f of, in this case actually f of 2, is equal to this thing f of negative 2. But we don't have the case that these two the a and b values are the same. 2 is not equal to negative 2, so it's not one-to-one. And we're kind of here, I'm writing down the definition, but basically what we're checking in this case for a one-to-one function is we want to make sure that y values do not repeat. That is what gives us something that's one-to-one. And so here we have another relation where this is kind of the domain and this is the range. And what we're checking is whether the same y value comes from two different x values. And you can see that actually it does not. This would be a really nice example of a one-to-one relation, because you can see that one thing from the domain will be mapped to one thing from the range. And so that is the idea for checking these ones, just based on these kinds of set notations. With this one is kind of a abstract sort of a set notation as well. We can check also for a one-to-one function if we are given the graph of a relation, this time by using the horizontal line test. And so here we see again another similarity with checking whether a relation is a function, where we used the vertical line test. Here, to check for one-to-one function, we will use the horizontal line test. And so we would want to find out if we draw a horizontal line through this relation, is there ever a time where that horizontal line will cross the graph in more than one point? And we can see for number 3, horizontal lines through here, they will not cross the graph more than once. And so it is one-to-one. And then if we see this graph over here with kind of this wavy one, if we, and I'm sure that this is a mistake of the computer here showing this extra line that's going across here, either way, this would not be one-to-one, because if we draw a horizontal line across here, we will end up crossing the function, or at least we will cross the graph of the function, I should say, in many places. And so this one is not one-to-one. And then here, another, I'm sorry that these graphs, they're not showing up properly. This one I believe is supposed to be one-to-one because it seems like it's graphing something similar to this, where horizontal lines will not cross the graph more than once, except for, obviously I drew it a little bit funny on this side. I think we're going for one-to-one, but you get the idea. It's the horizontal line test this time. And you might be asking yourself, what's the point of having a one-to-one function? Well, here is a little note to think about with one-to-one functions. If you have a function that is one-to-one, a one-to-one function will always have an inverse function. And so we're beginning here our discussion of inverse functions for section 4.1. And it's necessary to understand that not every function has an inverse function. And we want to check for a function to be one-to-one so that we will know ahead of time that a function that we're expecting to find an inverse function for that function. I know I'm saying the word function so many times here, but this is the idea. A one-to-one function, it will have an inverse function. Functions which are not one-to-one, their inverses are not functions. And so we will see that here. I'm going to scoot down a little bit because I want to show how we can check here whether a function is one-to-one based on the equation. And we're wanting to use, like I said, this version of the definition, where we will, basically what we're trying to do is we will plug in a and we will plug in b into this function. We will set equal f of a equals f of b. And then we want to basically simplify this thing, and over the course of this simplification, we want to arrive at this type of a statement, a equals b. And so then we will have basically that if the two y values are equal, then we can show for sure that that means that the two x values are equal. And so why don't we give it a shot? What is f of a whenever f of x is 3x plus 2? Of course, we should just plug in a, 3a plus 2. And then we're plugging in b as well for x, so 3b plus 2. And we're looking at this one just trying to simplify around, see if there's any kind of a way that we can twist this one around and end up having that a equals b. And it looks like this is actually going to work. If you can kind of see down the road what we're going to get at, we can just cancel the 2 off of both sides by subtracting 2 from both sides. Then it will go like 3a equals 3b. And then we can just divide by 3 on both sides. The 3's will cancel, and we ended up with this statement, a equals b. And so this one is one-to-one and checks out. What about the one for number 7 though? We want to start the same way. We're going to set f of a equal to f of b and see if we can arrive at this kind of a statement, a equals b. And so what we would do is first just try plugging in a for x. It will go 3a squared, and then f of b, it will go 3b squared. And now we can divide both sides by 3. It looks like we're getting somewhere with this. the 3's will cancel. This one goes a squared equals b squared. So we're trying to make some type of a statement about a and b, and so what we should do, we don't want the squared, we want to get rid of squared, so we should take square root on both sides. But here this is a problem, because when you have something squared and you take the square root, actually you will get this situation where you need to introduce the plus or minus signs, because of course 1 squared is equal to negative 1 squared. So if you just take the square root on both sides, then it's not really safe to do so, because you might end up with a funny equation. And so what this is, a is equal to plus or minus b. This actually gives us two equations, is that a is equal to b or a is equal to negative b. This one splits up into actually two different equations like this. And so you notice we were not able to say actually that a is equal to b, because it might be the case that a is equal to negative b. And so this one, it is not 1-to-1. And this is another way that we can write 1-to-1, by the way. And so that's how we will do it from the definition. It's very nice to try some of these. But anyway, we're going to get into some more things about inverse functions. We will eventually be finding inverses of functions, and that will be taking place in future videos. So thank you guys for hanging in there with this one, and I'll see you in the next one.